Right. Now we are on the third part. And in continuation to what we discussed about probability, we are now going to apply that in what we call probability distributions, which is very important in data analysis. Okay. So in the first place, what are probability distributions? So it says here, these are functions that describe the likelihood of different outcomes occurring in an experiment or random event. So, for example, in the dice, the chance of getting one, a two, a three, a four, a five, or a six, will be measured and then tabulated and even visualized in a graph like this. Okay, so probability distributions represent the probabilities of all possible outcomes to provide valuable insights into the uncertainty associated with various engineering parameters. Because we have uncertainties, what we can do is just based on their likelihood, okay, of the different outcomes. So we measure them. We we observe the pattern. Okay, and this is crucial in data analysis for making informed decisions and predictions, as well as in analyzing and modeling uncertainties. So, in short, we are applying the rules of probability, the concepts and the rules of probability to come up with analysis based on likelihood. Okay. In probability distributions, we have what we call random variables. Those are variables whose value is determined by the outcome of a random event. And they can be classified as discrete or continuous variable depending on whether their possible values form a countable set or an interval. So remember, countable, when we count things, we are just basically um, um, using discrete values. Okay. And if they are not countable, meaning there's an infinite amount of possible values, then that's continuous. Um, if we are handling discrete variables, then our distribution is actually discrete distribution. And if our variables are continuous, then uh, we are handling a continuous probability distribution. Okay, to explain that more, let's take a look at these examples. All right. So okay, it's kind of mixed. We have some of the most commonly used probability distributions in data analysis. So we have the normal distribution, which is our focus for the entire course. Um, and then other types of distribution are students T distribution, binomial distribution, Poisson distribution, exponential distribution, and so on. So let's take a look at some of these. Um, in terms of their defining characteristics, um, normal distribution is somewhat like the perfect curve. Okay, Gaussian curve. It has a distinctive bell-shaped curve, smooth like butter, and it looks like a bell. Okay, but a shorter and fatter version of this is the student's T distribution. Right? That's more advanced, especially in the case of what we call non-parametric statistics. Okay? In our case, by the way, we are dealing only with um, parametric statistics, or let's say the basic type of statistics. Okay, so the both of these are considered, or they fall under the continuous distribution type. And another continuous distribution is the exponential. So it models time between events. Okay, we are not going to use that actually in this course because again, our focus is more on the normal distribution. Now, when it comes to discrete distribution, two of the most common ones are the binomial distribution and the Poisson distribution. Binomial has only two possible outcomes, while Poisson has more than two. Okay, it could have various shapes and valid only for integers on the x-axis. Okay, um, we have their applications here. You can take a screenshot if you want. Okay, we're not going to discuss them one by one. Okay, right? So, okay, let's take a look at some of the properties and characteristics of probability distributions. Um, in discrete probability distributions, we usually measure our outcomes in terms of PMF. The PMF, or the probability mass function, assign probabilities to discrete values, especially integers, denoted as P, um, parenthesis, capital X equals to X. So capital X is a random variable, while X is the specific outcome for a given scenario or a given event. Okay? And the sum, take note, the sum of all of our PMFs must be exactly 1. Okay? So when you have your table of all the PMF of a certain sample space, all the events, all the PMF of those events, if you take the sum of them, that the sum must be exactly 1. Especially in the case of um, binomial binomial distributions. But in the case of Poisson distribution, it is somewhat um, just approximately 1, because there are some what do you call this? There are some approximations, there are some rounding off that take place along the process. And in binomial, it could always be 1, but in Poisson, most of the time it's almost 1, and we just round it off as 1. Okay? So on the other hand, in continuous probability distributions, we have the PDF, or the probability density function, which describes the relative chance of different values occurring, denoted as f of x. So here we are not just counting, we are taking the sum of all possible outcomes. The infinite number of possible outcomes must be added together. That's why here we are not no longer just doing the summation sign. Instead, we are doing the integral sign. Because remember, whatever the curve of your probability distribution, the area under it will be your total PDF. Okay? And that will be exactly equal to 1. Okay? So the integral of the f of x will be exactly 1, right? While the sum of all the p of x will be equal to 1 in discrete. Okay? So one very important thing that we usually deal with when it comes to statistics is the mean. Okay, so mean is such a very common thing, but take note, the mean that we know is usually applicable only in normal distributions. Okay, that's why in normal distributions we have the expected value equal to mean. Okay? While in other types of distributions, we have different formulas for that. And these formulas could be not enough. There are many other formulas. There could be any other formulas for the different types of distributions, as well as their variance, and then their CDF. Okay? So we're going to have more of this um, um, more about probability distributions when we get to our module 5, wherein we discuss this in graphical approach. Okay, these are not meant to be written manually or computed manually, because these things are too complicated or too lengthy. Okay, when we do manual calculations. That's why it's best to make use of tools like Excel and Python to understand how probability distributions work, and how can they be useful in data analysis. Okay, so that's it for now regarding this topic.